Hello all. In this video, we'll talk about the method known as Gaussian elimination and back substitution. A typical question in your exam or a homework assignment will look like this. You will be given a system of linear equations and you'll be asked to apply Gaussian elimination and back substitution to find a solution. We can also verify our answers sometimes by substituting them back into the original equations. We'll look at this problem in today's video. Okay, before I begin, we recall the following strategy. We will construct an augmented matrix for this system and try to row reduce it. Now, by now, you all must be aware of the valid row operations that we can apply to any augmented matrix. Be mindful that we can only apply 3 of row operations. One of them is swapping 2 rows or multiplying a row by a scalar or adding a scalar multiple of a row to another. And so let's start this question and we write the augmented matrix for this given system of linear equations. And now I begin with the top left entry and I want to make this entry a 1. So think of the most easiest way that you can do this. I can multiply the whole row by a scalar. I can multiply row 1 by a -1, and that would give me the desired outcome. And I get this entry. Only row 1 is changed because we are only operating on row 1. Next, now that I have the desired input in row 1, I'm going to make everything below it 0. So I need to take care of these 2 entries. So I begin with this entry. And how do I make this one a 0? Think for a minute. So I'm making a change in row 2. That's why we write row 2 here. I'm making a change in row 2. And what am I doing? I'm allowed to add a scalar multiple. So I'm going to add a negative of this entry to row 2. Now you cannot just operate on one entry. You have to subtract row 1 from row 2. So each entry will be changed in row 2. So I just copied down row 1 here and row 3 here. Row 1 and row 3, row 1, row 3 do not change because we're only operating on row 2. So I subtract the -1 from here, subtract -2 from 0, -4, subtract -3, you get -1, and this entry becomes 0 also. Now I'm done with, I have a 1 here and I have a 0 below it. So this is done. Now I have to make this -4 a 0. So what am I going to do? I'm going to operate on row 3, add 4 times row 1. So you see why we make a 1 to begin with, because now all I have to do is look at the number here, look at the sign, and add or subtract the scalar multiple accordingly. So we always begin with the 1 on top because that's the most efficient way. That is the efficient algorithm that you will be using throughout this course. Now I'm going to be adding 4 times row 1 to row 3. And what do you get? So add 4 times row 1 to row 3 and you got 0, -3, -8, you got -11, 2, -6, you got -12, you got -10, -3, -4, you got -7. So look, we begin with the upper left corner and we got that entry to be a 1 and everything below it to be 0. Now we again repeat the process here. But if you notice, we don't have a pivot entry. This is a non-zero. This is a 0 entry. So what is the easiest way to get a 1 here? This is where you'll use the row swapping technique. So the easiest, the most efficient way of getting a 1 in a pivot entry would be row swapping. And that's what we are doing here. We got a non-zero entry in row 2, column 2. And now I begin with the steps again. I need to make this a 1. So what do I need to do to make this a 1? I multiply by a scalar. So I multiply by -1/11. This guy is a 1. Each entry in row 2 will be changed. No change in row 1. No change in row 1. No change in row 2. But everything in row 2 will be changed, right? Even the augmented parts. Now, next, now I'm done here. I have a 1 here, zeros below it. I have a 1 here, 0 below it. I have a -1 at the last entry. I need to make it a +1, which is very straightforward. Multiply the whole row by a -1, and nothing will change above. Now this is the reduced augmented matrix using the Gaussian elimination. Now, I still need to solve the system. So what I'll do, I'll rewrite the reduced augmented matrix into a system of linear equations. So I begin with equation 1. This is x1, -2x2, -3x3 equals -1. The second row gives me the second equation, x2 plus 10/11, x3 equals 7/11. The third equation, the third row of our reduced augmented matrix gives me the third equation, which is x3 equals 0. And now you see, solving for values of x1, x2, x3 becomes easier. So now I have x3 equals 0. I substitute. So I start from the last equation because that's the easiest, and hence the name back substitution. Start with the last equation because that's going to be the easiest always. That will always be the case with the last equation, and start with the back substitution as it is the simplest. And there you go. I substitute x3 in equation 2 and I solve for x2. I get this answer. I substitute x3 and x2 in equation 1 and I solve for x1. Some basic algebra going on here. Solve for x1. So you see some basic algebra going here, and we are simplifying for x1, x2, x3. And you see the point of using back substitution. We start with the last equation and work our way up. And now, once you have x1, x2, x3, we can also verify our answers by substituting these values in the original equations. So you go back to the question, substitute x1, x2, and x3, and check if your LHS equals RHS. And it must be true for all equations, must hold for all equations. And there we go. This is the end. So you will be asked to verify your solutions in some questions, or you will simply just asked to solve a system. I recommend when you're solving a linear system using row reduction, try verifying your answers yourself so to see if you're on the right track or not. But this is how we simplify a linear system using Gaussian elimination and back substitution. See you in next video.